So starting chapter 6, and chapter 6 is probably going to seem a little bit more unfamiliar, a little bit newer to you than most of the rest of the class. Most of the rest of what we've done should have mostly been review from Algebra 2 and maybe some extensions of what you did in Algebra 2, but still similar things other than the chapter on matrices that we did. Chapter 6 is probably going to be all brand new for you. Chapter 6 is all about just kind of different ways to represent things. Today we're going to be looking at vectors. So I'll start with this note down here about what the point of vectors is. So vectors, we often use them in physics to represent things that have a magnitude and a direction. So the idea is if you just have speed, if you just look at the speedometer on your car, it says 65 miles an hour. All that tells you is how fast you're going. You have no idea what direction. Is it north, south, east, west? Is your car in drive or in reverse? Hopefully you're not going 65 miles an hour in reverse, but you don't know just by looking at the speedometer. And so we want something else besides just speed. We call it velocity, something that incorporates both how fast you're going, your speed, which we're going to call magnitude, and also the direction that you're traveling. That's going to be called a vector. We also use vectors for force. So if you hit a baseball, the force, we would want to look at both how hard you hit the baseball, that would be the magnitude, and also what direction did you hit the baseball. Did you hit it straight up for a pop fly? Did it go right into the ground as a ground ball? As a line drive straight ahead? The force, the magnitude, and the direction are important, and that's what we can represent with vectors. Now the thing about vectors is they're often going to look kind of just like a point. We just use angle brackets instead of parentheses. But we're not just looking at a point, a dot in space. We're looking at some sort of motion or force from the origin to that point. There's some sort of motion or directed force going on right here. So we use arrows to represent that. But if we know what point we ended up, if we know we started from the origin, then we can represent the vector just by the x and y of where we ended. We use those angle brackets to say that we are a vector. And then the magnitude is going to be the length of this line here, the length of this arrow. It's going to be like the hypotenuse or the radius. And then the direction is going to be represented by the angle. And so, of course, we've got lots and lots of relationships between all of these things. So before, what we said was that cosine of theta was x over the r, or the hypotenuse. And here we're going to call it the magnitude. We use absolute value bars to represent magnitude. And so what we're going to do is we want to be able to find the x and the y based on the magnitude and the angle. So we just solve for x. We multiply the magnitude over and get a nice formula for x. We can do the same thing with y. And of course, we could look at this as a reference triangle right there. We've got our x here and our y here. And so if we want to find this magnitude from the x and the y, we've got our little Pythagorean theorem relationship. X squared plus y squared is the magnitude squared. And so that's where we get this formula for the magnitude here. We square root both sides. And when we square root both sides, we don't need a plus or minus here. Your magnitude is going to be always positive. Just by definition, magnitude is always positive. Again, magnitude is kind of like speed. We don't have negative speeds. We just have how fast we're going. And then for the direction angle, there's lots of things that you could use that involve theta, but we usually want to find theta just based on the y and the x. And so we're going to use tangent for that. And we've got this note here. We're going to have to check quadrant. We're going to have to talk about that a little bit more coming up. All right, so let's look at an example here. So let's say we've got the velocity vector of a plane. It's 237, 428. And so what this represents is how fast the plane is moving in two different directions. So if we just looked at the horizontal motion of the plane, how fast it is going sideways, that 237 shows you how fast it's going in the x direction. And then the 428 shows you the vertical speed, how fast the plane is rising. This is rising at a rate of 428 miles per hour. Now let's say we want to know the overall speed of the plane. Well, speed is going to be the same thing as magnitude. So we just want to find the magnitude here. A lot of these problems, we're just going to be using these four highlighted formulas right here. So magnitude, we just want square root of x squared plus y squared. So square root of 237 squared plus 428 squared. And we can definitely use our calculator for that. Square root 237 squared plus 428 squared. So the plane is flying almost 500 miles per hour, about 489.237 miles per hour. Okay. So then if we want the direction angle, we want the theta. What we want to do is just use the x and y. We don't want to use this approximated speed, this magnitude right here. And that's why we use tangent to find our angle. So we're going to do inverse tangent. Remember that tangent is y over x. So it's the 428 over the 237. And so we'll just stick that in our calculator here. And I'm in degree mode, so that's my angle in degrees. Vectors tend to be done in degrees. You're certainly welcome to do them in radians if you would like. We can do that right now just to show that if we wanted to switch to radians. Either answer would be perfectly acceptable. It just tends to be that vectors tend to be in degrees. Either one is fine. All right. And so what we do always need to make sure we do those, just check the quadrant. Because again, inverse tangent is a function. It has to only have one output. And so there's lots of angles with that tangent right there. The calculator just picked one of them. Let's see if it made sense. So if we look at this vector right here, both the x and the y are positive. So that means that we are in quadrant 1. Well, we've got a quadrant 1 angle here and a quadrant 1 vector there, so that is the correct angle. That one does make sense. And then one of the reasons that we like vectors that we use a lot in physics is it's really easy to combine vectors together. So let's say that wind starts blowing with this vector. To find the new, we call it the resultant velocity vector, what happens when the wind kind of blows the plane off course. All we have to do is add them together. So we can take the plane. A lot of times you'll see kind of a little half arrow above things to represent that it's a vector. In printing, we'll use bold type, but you can't really use bolds when you're writing. So you'll often see a little half arrow. And so all we have to do is add the plane and the wind vectors together. And to add vectors together is kind of like matrices. This is just the easiest thing that you could think of. You just take the x's, add them together, and take the y's and add them together. You just add the corresponding elements. And so this is going to be 237 plus negative 12 and 428 plus 23. And so we get 225 and 451. And so that's the plane's new velocity after the wind started blowing it a little bit. All right, and so if we kind of step away from a context here and just look at it abstract, I'll talk about the i's and j's in a minute here. But first of all, to multiply a vector by what we call a scalar, something that's just a number, just like matrices, it's super easy. You just kind of like distribute, just multiply the x and the y, both components, by the 3. So we've got negative 6 and 15. Super easy. So what about the i's and the j's? So the I and the j are what we call standard unit vectors. This is just another way of writing vectors. So actually what happens is this 3i plus 4j, all that means is just 3 comma 4. The I tells you the x, and the j tells you the y. That's it. So I is, so unit means 1. So we've got vectors that have a magnitude of 1 that are only a distance of 1 away from the origin. And I is in the x direction, j is in the y direction. And so any vector can either be written in what's called component form or what's called a linear combination of the standard unit vectors, the i's and the j's. But just don't get freaked out. What's next to the I is the x, what's next to the j is the y. If you want to see why that is quickly here, what we've got is the a times I. Well, that's a times 1, 0. And then b times j, that's b times 0, 1. Well, if we multiply those in, that means we've got a0 plus 0b. And so you can see that's going to give you right there, a plus 0 is the a, 0 plus b is the b, and so it works out nicely. But you don't have to worry too much about that. The I is the x, the j is the y. That's it. So then to do what we're asking you for here, 2v, just take the v, multiply it by 2. So we've got 6, 8. Because we wanted v first and then u second, watch out for that. And then for the minus 3u right there, you could multiply by 3 and then subtract, as long as you're careful with your subtraction. But I find it a lot easier when you're subtracting to just add the negative. So I'm going to multiply by -3 and then add the vectors. And you don't have to do that, but I find that makes for less mistakes. Again, we just add the corresponding components, add the x's together, add the y's together. And so we've got 12 and -7. All right. And then our last couple problems here, what we're going to do a lot is just kind of go back and forth between the x and the y and the magnitude and direction, between the magnitude and direction and the x and the y. So here we have the x and the y. Again, -2i plus 5j, all that means is -2, 5. Don't let the i's and the j's freak you out, nothing to it. And so if we know the x and the y, all we got to do now is just use these formulas. Again, I highlighted them for you up here. These 4 formulas, just make use of them a lot. So magnitudes come from the Pythagorean theorem. Square root of x squared plus y squared. Magnitudes, square root of -2 squared plus 5 squared. Make sure that -2 squared turns into +4. -2 times -2. And so we get root 29. And of course, you could leave it like that if you wanted to. That'd be fine. You're also welcome to use your calculator, turn it to a decimal. Either way would be fine. So this is about 5.385. Right, so then our direction angle, again, we want to try not to use this ugly magnitude here. Maybe we made a mistake, and so we don't want to carry a mistake forward. Just try to use what's given. And so to find our angle, we're going to use just the y and the x, use tangent. And so we're going to find inverse tangent of 5 over -2. And I'll just do this in degree mode. You could do radians if you wanted to. And so my calculator tells me that for the angle. Now the fact that it's a negative angle is not a problem. You could always add 360 to it if you wanted a positive angle, but that's not really an issue. However, there is a problem. That's not the correct angle. Let me write this down for us. The calculator said -68.199 degrees. That is not correct. That is not what theta is. Remember, this note up here is very important. You must every time check the quadrant. Your calculator is a tool. You've got to use your brain alongside the tool. Right? Check the quadrant. The quadrant that we have here does not match the quadrant of our vector. So -68 degrees, that's less than 68 is less than 90. That would be a fourth quadrant angle. That's not much rotation, and we just rotated backwards into the fourth quadrant. Take a look at our vector. You always want to compare your angle with your vector and see if they're in the same place. This vector right here, we've got a -x and a +y. That vector's there in the second quadrant. This angle that we're looking for is right here. I mean, we could find a negative angle if we wanted, but either way, it's not going to be -68 degrees. All right? So the 68 degrees is actually our reference angle. We know that this angle right in here is about 68 degrees. So to find the angle that we want, to find this theta, we have to start at 180 and then go backwards about 68 degrees. Theta is going to be about 180 minus that 68 degree reference angle. Of course, on my calculator, I've got it as negative, so I want 180 plus that negative 68 degrees. So I'm just going to take this angle that I found and add 180. And that's my angle. That's a second quadrant angle. That angle matches where my vector is. Always, always, always check that what you started with and what you ended with are in the same place. That's going to be very important this chapter, is what you started with and what you're ending with in the same place, in the same quadrant. And then the last problem here will be really easy. We just got to plug and chug into some formulas. We've got magnitude, we've got the angle, component form. Again, component form is just the x and the y. Well, we've got some nice formulas for those. We just need to take the magnitude times cosine, magnitude times sine. So to find my x, I'm going to do 5 times the cosine of 207 degrees. Let's plug that right in my calculator. Make sure I'm still in degrees. There we go. So x is about negative 4.455. So x goes with cosine. We know that from the unit circle. Y goes with sine. It's the same thing here. We're using a lot of the same relationships that we've already used. We're just using them in a new construct called vectors. And of course, you can use second enter to go back what you typed before, or hit the up arrow and hit enter and just change that cosine to sine. Find your y. And then technically for a component form, we should write that in angle brackets. So finding x and y and the magnitudes are all really easy. The one that you're going to have to think about is finding the angle. Careful with those quadrants when you're finding the angles. The rest of this should be pretty straightforward. Just use those formulas. If you really hate plug and chugging formulas, I mean, you can draw these things out. You could say you had a 207 degree angle. So you were right there. You could draw a triangle. You could use all those relationships. You could find your reference angle if you wanted to use a SOHCAHTOA and a right triangle, but you would have to think about the fact that you went left and down, so both x and y were negatives. You can draw this out and do all that, but it's a lot more straightforward just to use these 4 formulas. And we are going to have to make use of these for something else later in this chapter as well. So you might as well just start getting yourself comfortable with these formulas now.